Okay, let's get started. My name is Eric, and I'm a freshly defended grad student. I just finished my doctoral training, and it's a real thrill to be here to share with you some of the knowledge that I've gained over the past few years in network analysis and the likes. It's a topic that's close to my heart, and particularly because it's a tool that's been useful for my dissertation research. So before we launch into the actual material, I want to get people warmed up. And so let's try this little short quiz here. There's a list comprehension on the screen. And if you open up Notebook 1, you'll be able to see that as well. My question to you is, if I have this list comprehension, as shown over there, there are two variables for which I'd like to know what your thoughts are on a plausible data structure for those variables. They are S and my favorite things. So what could they be? Popcorn style, feel free to raise your hand. So dictionary for S and list for my favorite things. That's right. Are there any other plausible data structures? Pardon me? All right, so anything that behaves like it's got a selector syntax, right? So you can select into a key of some particular thing. So dictionaries, plain dictionaries are one, ordered dictionaries are another. I'm not sure if named tuples are allowed. I think they are allowed. You're allowed to use the selector syntax on that guy as well. Okay, corrected. And the reason is because the moment we connect, we're automatically bidirectional friends. What a technical term, bidirectional friends. What about Twitter? Twitter's directed because it's based on a following relationship. So you have unidirectional friends. You don't have bidirectional friendships. Yeah, all right. And then air traffic networks are an example of another directed network as well. Okay, so from this tutorial, it's my hope that you'll be able to do a few things in practical terms. So the first one is use NetworkX. This tutorial material is both conceptual and practical, and at the practical level, I've chosen NetworkX because it's a library that provides a simple API for the manipulation analysis of graphs. There are other graph libraries out there. I'm not going to go into them today, but you can do your own exploration. My hope is you'll be able to use NetworkX in the Jupyter environment to do network analysis problems. The second one is I'm hoping you'll be able to be convinced of the utility of not visualizing networks with hairballs. Right? I do not like hairballs as network visualizations, and I'm hoping to convince you of that as well. So there are rational visualization methods, for example, circos plots, hive plots, etc. I want you to be able to have some tools at hand to be able to do that. The third one would be to think through network algorithms. Right? So you don't have to, at the end of the tutorial, be like the most efficient algorithm writer, but I do want you to be able to think through network problems in an algorithmic sense, and we'll get a flavor for that. There's one particularly hard exercise in the middle of the tutorial which has caused many, many tutorial participants before lots of headaches during the tutorial, but a bit of coffee at the end will solve that for you as well. It's my hope that you will be able to think through network problems through this tutorial, all right? And the final one would be thinking through statistics that describe a network, right? So, the degree centrality distribution as a teaser is one thing. What's the distribution of connectivity over all of the nodes and that sort of thing, all right? From a broader perspective, so this is no longer practical but more conceptual, I'm hoping to convince you that our usual way of thinking about data, that is the rows of entities and their properties, that we can start thinking about these things in a relational sense, where we have relationships between these entities and not just entities themselves. So it's my hope that you'll take this back home to whatever domain problem that you're working on. And if we have the time, my hope is also that we'll be able to think through statistical problems in network analysis. All right? And statistical problems refer to the summary description of a network plus inference problems, which are a bit tougher. They require a bit of statistical thinking, so I might not go through it today. But there is a set of notebooks inside there that you can use for self-paced learning as well back at home. Okay, before we go on to the actual coding exercises, I want to give you a preview of the tutorial format. you'll notice from Notebook 2 through to Notebook 6, there are pairs of notebooks that have the same title but differ only by student or instructor. Your version is the student version, but you're not prohibited from opening the instructor version. If you ever find the student version exercises too difficult, you can actually look at the answer inside the instructor version. I'm not going to be offended if you do that. In addition, if I'm too slow for you in this tutorial, and you're having a breeze with all of the tutorial exercises, and you just want to self-pace yourself throughout the rest of the tutorial, by all means, don't worry about it. Go ahead. Again, I won't be offended. The notebooks were actually structured and designed to be self-paced learning material as well, especially for this year's updates, so to speak. And so if you want to take the time now to just zoom ahead and do your own thing on the material, totally okay. Otherwise, we're happy for you to join us at the rest of the class's pace. Okay, so with that, we're going to get started with the coding exercises. That's enough of me blabbering on. I'd like everybody to open up Notebook 2 on your laptops and follow along. Now, there's a whole bunch of, like I mentioned, the tutorial exercises and the likes are designed to be self-paced. So the rest of this, I'm intentionally not going to show slides versions of the notebooks. I'm just going to display the notebooks up on there to give you a rough feel for where we are. And I'll do whatever talking I need to do for each notebook and the exercises, but I won't particularly zoom in unless there's a particular exercise solution. Like I mentioned, the exercise solution, you can also find it in the instructor notebooks locally as well. All right? Everybody okay so far? Do we have any questions before we move on? All right, if there are no questions, let's get going. So the first set of notebooks, the first notebook that we'll do that involves coding is notebook number 2, and it's essentially an introduction to NetworkX. Right? It's just to get you familiar with the NetworkX API. So how do we represent relationships between individuals in NetworkX? Or in other words, how do we represent a graph in NetworkX? What I would like you to note is in NetworkX, the underlying data structure is a dictionary of dictionaries for nodes and a dictionary of dictionaries for edges. So you'll be using a lot of the selector syntax when accessing keys and when trying to access values that are keyed on some particular key. And this will become clear as we go along, all right? First thing I would like you to do is to load some data into memory. And so this network data set that we're going to take a look at is a social network of 7th grade students, right? So these little kids were asked to decide amongst their friends who they like. Right, and they had like 3 times to vote for a particular person or something like that, or 3 particular opportunities. So this is proximity ratings between students from 29 7th grade students in a school in some place called Victoria. They were asked to nominate their preferred classmates for 3 different activities. A node represents a student, and an edge between 2 students shows that the left student, right, so pick the right student as his answer. The edge weights are between 1 and 3 and show how often the left student chose the right student as his favorite or her favorite, okay? All right, so if we have a graph in memory, there's a few basic tasks that we'll want to do as sort of a sanity check. We'll want to know what are the nodes and how many nodes are present. And so in order to get the nodes from a graph, so note we have a graph that's loaded into memory called G. There's a custom function that I've written. You can find it in the custom functions directory. And so with this graph object, we can ask, how many nodes are present? And the way to do this is to call on the .nodes method. So if I do g.nodes and I run that, oops, let me just run this one. Okay, I'll get back a list of nodes. Now these nodes can be any hashable object. An integer is good, a string is good, a a list is not good because the size of a list can change over time, is mutable, so it's not hashable. So in this case, our nodes are represented as integers. There are no names and no names attached. And what's the data structure of this guy that it's returned? It's a list. OK, good. So let's do a 1-minute exercise below. Can you write a single line of code that returns the number of nodes in a graph? So this one should not be too difficult. Take 1 minute and write that. And we'll, at 1 minute point, we'll double check and see how fast people are. OK, how are people doing? All good? Give me a thumbs up if you're good. All right, so you should have written something like len of g.nodes, and you should get 29. All right? So then we can also get so let's move on from this exercise. We can also figure out who's connected to who in the network by getting the edge list. So previously, g.nodes gives us the node list, and we can get the edge list by doing g.edges. And may I ask now, what's the data structure represented here? A list of what tuples? 2 tuples. It's important. The tuples are specified by a size as well, right? So they are a list of 2 tuples. And in each 2 tuple, each 2 tuple represents an edge. And the edge, and so we have the left node and the right node represented in there. And so that's the edge list represented as a list of 2 tuples. All right. So if you could move on and try the next exercise below, basically it's analogous to the first one. Get a single line of code that represents the number of relationships represented. So again, 1 minute. Okay, how are people doing? Can I see your thumbs if you're, give me thumbs if you're ready to move on. All right, I don't see thumbs from everybody just yet, or a big fraction of people just yet. We'll give it a little bit more time. If you run it, if you do something like len of g.edges, that will give you the number 376. That means there are 376 edges that are represented. All right, everybody got that? So basic statistics of a graph. We have the node set and the edge set. We can ask how many nodes are present and how many edges are represented inside the graph. OK, so what you've seen just now is the most basic minimal description of what a graph is. It's a set of nodes joined by a set of edges. And they can be represented as 2 lists. You can represent it as a node list and an edge list. And so the node list can either be a list of single elements or it can be a list of 2 tuples. And if it's a list of 2 tuples, it means that not only is the node being represented, there's also metadata that's also attached. Likewise, I mentioned the edge list can be represented as a list of 2 tuples, or it can be represented as a list of 3 tuples, which I'm going to show as well. And that third element in the 3 tuple represents the metadata dictionary that encodes the metadata associated with the edge. So let's take a look at that. If I pass in the data equals true keyword argument to the g.nodes method, then I will get back the metadata dictionary that's associated with that node. And so I can use a dictionary to encode all other information that I might want to know, right? So for example, let's say we have a class in this class of 7th graders. We have boys and girls inside the class, and so we have their male and their female gender, and so we can then encode their this information. We can even encode things like birth date. We can encode things like where their hometown was and that sort of stuff. Stuff that's metadata that's associated with a particular entity. So what I'd like you to try to do is to count the number of males and females represented in the network. And as a hint, you may want to use the counter object, which I believe I've imported for you at the top as well from the collections module. So we'll spend 3 minutes trying to write this code. And this code will give you a very good flavor for for the kind of coding pattern, again, that we'll be using. How are people doing so far? Okay. Do you have list comprehensions on your mind? That's the hint. You may want to use the counter object, but you may also want to use a list comprehension. Okay. So 3 minutes are up. Can I just get a quick sense for how people are doing? Thumbs if you're done. All right, we sort of have enough quorum to move on. So I'll very quickly talk you through the list comprehension. Note, so if you remember, g.nodes gives us a list of two tuples if we pass in data equals true. Of that two tuple, the first element is a node. We can use the loop variable n and to represent that. And the second element is the metadata, represent a dictionary. So we can use the loop variable d to represent the dictionary there. We're trying to collect the metadata that's keyed on the variable gender inside the metadata dictionary. So we collect all the values that are represented by there, and that gives us the list comprehension. And then we pass that entire list comprehension into the counter object, which gives us the male and female counts. And it'll count the number of times male shows up and the number of times that female shows up. And so we can then test the answer and check that it's correct, and we have that. And if everything passes, if you run the test answer function call and nothing happens, that means your list comprehension was correct. All right? Okay, so metadata can also be stored on the edges. And so quick recap, this is not a trick question. What's this data structure that I'm highlighting? Or it might be a little too small. What's the data structure that's represented up here on the screen over here? It's a list of 3 tuples, exactly. All right, so can you find out then? So this third element here is this third element here is the metadata that's associated with the edge. You can have metadata like things like counts. So if each edge is actually a summation of multiple counts of some relationship between the two, you can have metadata called count or weight that's associated there. If we're talking about a social network, you can talk about things like what date was this friendship formed. Then you can attach a date-time object in the middle over there as well. Okay? So in the synthetic social network, the number of times the left student indicated the right student was their favorite is stored in the count variable. So I'd like you to write a bit of code that figures out the maximum times that any student rated another student as their favorite. All right? So we'll take another 3 minutes for this exercise as well. I don't know the exact details of the study, but the rough setup is described above in the notebook, and it's basically, I think, 3 separate occasions. Each student is allowed to rate friends or something like that, and they can rate a number of friends or something. So there's a bit of background. And if you'd like more information, that's actually, I have the data credits that are listed in the README file, and you can look for the exact same data set on the Connect website. All right, so 3 minutes roughly is there. Does a list comprehension come to mind as well in this particular case? Right, so if you had, just want to double check again, how many people are done? Give a thumbs up if you're done with this one. Okay, roughly the right pace here. That's great. Okay, so the answer is shown here. Again, we have g.edges, which gives back 3 tuples. So in the loop variables, we can use n1, n2, d, or network X convention. In the documentation, uses u, comma v, comma d. U for the u and v for the vertices, which is another name for the nodes. And then what we're trying to do, though, is we're trying to collect the count, the value keyed on the key count in each of the metadata dictionaries. And so we collect all of that together, and then we get max, and when we get max count is the maximum value of all of these numbers. And if the max count is 3, then you run that test function, that should be okay. All right, so the next part is a little exercise that is designed to get you a bit more familiar with the NetworkX documentation. And so what I'd like you to do is this following exercise here. We found that 2 students were left out in the network, and they're individuals number 30 and number 31. They are one male, which is individual number 30, and one female, which is individual 31. And they are a pair that just loves hanging out with one another, and they love hanging out with individual number 7 as well. And so that means the count equals 3 is attached to all of those edges. So I'd like you to add this information into the graph. So use the NetworkX documentation to figure out how to add edges and add nodes. And I believe I've provided you a basic a basic outline of the code that's required over there. So we'll spend 5 minutes on this exercise. That's better. Just want to do a quick check in case this exercise didn't need 5 minutes. How many people are done with this one? Okay, we'll give people a bit more time. Maybe we'll go to the 3-minute or 4-minute mark. All right, quick check. How many people are done? Thumbs up. Okay, I think we've got quorum, so let's move on. This is the brute force way of doing it, where you add every single edge one by one. The idea was just to get you familiar with the add edge and the add node function calls methods. So we can add node and we can add in keyword metadata in this particular fashion. Likewise, we can add an edge. We pass in the first node and the second node, and we can pass in metadata in this fashion as well. And if this were an undirected network, this isn't, by the way, from the description. The left student has to indicate the right student, so the right student might not necessarily indicate the left student as their favorite. If this were an undirected network, then you could get away with adding just each of the pairs. So note you'll have to do 30 with 31 and then 31 with 30 as well if you want to add this information into a directed network. With an undirected network, you can get away with just adding one of them. All right, you don't need both. You don't need both of the edges to be added in. All right, so this is a little detail to take note of. And if you look at the test graph integrity function, you'll notice a few things that are going on there. So first off, we're using the selector syntax to access the metadata or to access the metadata dictionary. If we wanted just the dictionary, we could do g.node and then put the node number in. And then what that returns is a dictionary, which then we can select into again for the keys. There's a function or a method call that exists inside each graph object called hasEdge. So we can look for every edge inside there. And then we can look for the metadata that's associated with each of the edges. And so you'll notice there's a selector with another selector with another selector, which tells you it's a dictionary of dictionaries. Is that right? It's a dictionary of dictionaries, actually. Triple layered dictionaries for storing the graph information. All right? Quick note about tests. Testing is good practice for code writing, and I really highly encourage you to write tests. It falls under this realm of defensive programming. Software Carpentry has a very good resource on this. I encourage you to check up that. Okay, so we showed you a few coding patterns. I'm hoping that by this point, the list comprehension should be quite up there in your mind, right? So when you think about Network X, the list comprehension is a very convenient way of getting information out of the network, right? So you can have things like, for node lists, you can do d select attribute for nd and g.nodes, passing in data equals true. Note the nice underscore escaping out a variable type of syntax where if you're not interested in the node, you can just forget about that and put an underscore there. Likewise for edges. So say, for example, if we're interested in getting all edges of a particular, or sorry, if we're looking at every edge in a directed graph, for example, and we're only interested in nodes that operated as sinks and not as sources, then you can do syntax like this, where we say n2, which is the sink for every edge in g.edges. And if we pass in data equals true, then we'll either need to have this extra d loop variable, or we can ignore data equals true and just forget about the d and just have underscore n2 or n1, n2, okay? That sounds okay with everybody? The list comprehension is really the main idea here. We'll probably be writing a lot of list comprehensions. Okay, if we scroll down, there's a bit of information on basic drawing of graphs, and this is sort of the place where I want to brainwash everybody or use propaganda to, it's not alt-right, don't worry. I want to use propaganda or brainwash everybody to stop using hairballs. Hairballs are a bad thing. And what do I mean by hairballs? I mean this, right? This is the social network, and it's a hairball. You just can't tell a lot of stuff from that network except for this probable little outlier thing that's out there, which refers to the two nodes that we just added, right? So if you run this cell, nx.drawg, I forgot to run that other stuff, didn't I? Let me add this in. There we go. If you run that cell, you'll notice that little triangle at the top of your notebooks as well. And that basically refers to the edges that we just added. And nx.draw, for small graphs, you know, I'd say nodes less than 10 in size. It's fairly good. You can pretty clearly see the edges and the connections between nodes. But anything more than 10, it's really hard. So this is most useful perhaps when we're looking at a subset of nodes in a larger graph, right? And we'll have an exercise that takes advantage of that. But this here, it's a hairball. And the hairball can be compounded if we add on with labels equals true, and we ask to label each of the nodes, and oh my gosh, it's a crowded visualization. So basically the idea here is unless you're visualizing subsets of a graph or unless your graph is really small, don't use the hairball. It's a bad visualization. It's very uninformative. Instead, I want to introduce you to a little bit of this package that I wrote because I was frustrated with the state of network visualization in Python. There were tools available outside for other programming languages and nothing available for Python. So I thought, okay, those visualizations exist. Let me just try implementing them in Python. And so NXVis was the product of all of that effort. It initially was two separate plotting modules called HivePlot and CircosPlot. And then there were some generalizations that I realized could be made and an API design that could be really, really nice for end users. So a bunch of my friends and I who are in the scientific Python community, we just thought, let's just build it. And so this is the product of that. So we can start by looking at a matrix visualization of networks, where in a matrix visualization, every row is a node, and every column is also a node, right? And so if we order the nodes in the exact same order on the rows and columns, then we can represent whether an edge exists between those nodes by coloring in that cell that indicates that keys the row, the particular row and column. And so we get something like this, right? And it's the matrix form of a graph. It does not necessarily have to be ones and zeros. You can put floats on there. Say, for example, if you have weights or if you have counts that are associated, this is just the binary form where we have 1 indicating an edge and 0 indicating no edge, or blue with edge, 0 without an edge. And immediately it's clear, if you look at the diagonal of the matrix, you'll notice, yeah, there's no self loops, right? There were no narcissistic 7th graders that said, I like myself, and I only liked interacting with myself, which is sort of a good thing, right? We don't want to raise a generation of narcissistic youth. So that's the matrix representation. If it's a directed graph, what will be a special property of this? If it's an undirected graph, what will be a special property of this matrix? What do people think? Exactly, it will be symmetric around the diagonal, right? And so you can actually use half the information, half of the number of cells to represent an undirected graph. If it's directed, however, then we have to be clear whether the rows are the sources or the columns are the sources, right? The starting point for the node, for the edge, and the end point for the edge. We have to be very clear about that definition. Okay, so if you run that cell, you'll get that on your notebooks. Another visualization that I'd like to introduce to everybody is called the Circos plot. All right, and the Circos plot is a very beautiful visualization. By the way, in case anybody's interested, it took me plus another MIT undergrad working together for a good whole afternoon to figure out the right implementation in Python. So big credit goes to Justin Zabalansky, who's the undergrad who worked with me on this, and another buddy of mine from the Boston Python area, John, who introduced styling onto the Circos plots. And so, for example, if you run the next cell below, it'll take a little while, you'll get something that looks beautiful, right? Very informative. You can group and order nodes. So, let me backtrack a little bit. The way a Circos plot is drawn is that we place all of the nodes on the circumference of a circle. You can then apply grouping and sorting operations to those nodes. You can group them by some property, or you can sort them or order them by some property. And then only after grouping and sorting the nodes do we start drawing the edges between those nodes. And we draw them as arcs within the circle. And so what comes out is this very beautiful visualization. It's gorgeous. When I first saw Circos plots, I was blown away. And I was wondering why this didn't exist for Python. And so I worked with Justin and John to get this into Python. And so that's the result. The API call is up there. From NXViz, we instantiate the Circos plot. We pass in the graph, just like, I forgot to explain the API for the matrix plot as well. It's very, very similar. It's a declarative API. And so the idea is we instantiate the plotting object, and then we pass in the graph object, and we just tell the Circos plot constructor, how do we want to color the nodes? We color them by some keyword that's on the node metadata. How do we want to group the nodes? We group them by some keyword that's on the metadata dictionary. All right? And then we draw it, and then we draw it to screen, and then we can save it. It's a matplotlib object. It's built on top of matplotlib. So if you're familiar with the internals of matplotlib, you can get the axes object. You can iterate over all of the children objects that are inside there, customize the styling for yourself. This comes with nice, sensible defaults, but it's fully customizable under the hood using matplotlib. Okay, so that's the Circos plot. And this visualization actually can help us look for the loners in class, right? So something like this node over here, this student and this student over there, they're sort of the loners in the class. They don't have a lot of friends. But why was that the case? We just added them, right? Nodes 30 and 31, and we forgot them. But then when we looked at the data, we found, they only like hanging out with that other node, node 7. So that triangle relationship is represented here. This this purple node to this green node to let's trace it, I think it's this purple node over there, right? And that triangle relationship is represented there. Okay, so this visualization helps us organize the nodes, and actually all of these rational visualization methods that give nice diagrams prioritize the placement of the nodes over a random, instead of doing a random arrangement like in the force-directed layout, for example. And this prioritization of the nodes gives a lot more structure to the visualization. The final one that I want to show you is called hive plots. Now, hive plots have not yet been moved over into NXViz, so this is mostly for concept. Don't look at the code. Don't follow the code. That code is deprecated. I just wanted to get you a flavor for what hive plots look like. They essentially look something like this, right? And so what are we seeing here? We're seeing the nodes, again, grouped by some particular category. In this case, we have the male-female category, right? And then we have all of the nodes from one category on one axis at the top, and all of the nodes from another category on the bottom axis at the bottom. What we're seeing is essentially this. If we have if we have edges that are represented as a within group type of edge, then what we can do is we can take that top axis and that bottom axis, clone it, so that now we have cloned axes, and then draw edges between them to represent intra-group edges. And then we can look at inter-group edges by looking at the left-hand side of the screen, where we see the edges coming from these nodes over here, which are identical to these blue nodes over there, and they're intra-group edges represented between the red and the blue nodes. All right? So that's the idea behind hive plots. It's another rational way of visualizing it. And shortly, soon after, hive plots will be implemented as, well, I've got time since I've defended now, so I can start implementing this into NXViz. Right? But if you're interested and you'd like to help make this happen, or make other contributions to NXViz, the package is on GitHub under my username, and I'd welcome any contributions that you might have, even for documentation. Documentation is poorly done right now, so even docs would really help. Okay, so with that ends our tour of the basics of the NetworkX API and a tour of some of the ways of rationally visualizing networks. And I'm hoping that this short little section on rational visualizations has given you inspiration to go forth and dream up other rational ways of visualizing networks, like, say, arc diagrams or flow diagrams, for example, that prioritize the placement of the nodes over the placement of the edges, okay? Okay, so with that, I'd like everybody to move on. Let's open up notebook number 3. And run that first cell. Let me just run everything first. And in this notebook, notebook number 3 is called Hubs and Paths. And in this notebook, we'll be doing a short tour through how we can look at node importance, and how we can think through some graph algorithms. All right? Okay, so run that first cell to get everything imported. Let me toggle the header. And what I'd like you to then do now is to load the data. What's this data? It's a data of face-to-face contact between participants at an infectious disease exhibit. Right? So nodes represent exhibition visitors, edges represent face-to-face contacts that were done for at least 20 seconds during that exhibition. Multiple edges between two nodes are possible and denote multiple contacts, but in this particular case, I think I've condensed the multiple contacts into a single edge between them rather than having multiple edges. And the network contains the data from the day with the most interactions and not the whole full time frame. All right? So run this cell over here, cf.load social patterns network, and we can do our sanity checks then to say, okay, how many nodes are represented and how many edges are present inside that network. Okay, everybody's gotten those two lines run? Okay, so we're going to talk about firstly how we evaluate the importance of individuals in a network. If we have a social network, let's just brainstorm for a short while. If you have a social network, who would you consider to be an important person based on that person's so-called connectivity in the network? What would you think might be a plausible way of, or a possible way of evaluating a person's importance? Number of edges, incoming or connecting that node to other nodes, right? Okay, yes, so that's one way to look at it. And in that way is essentially, so if you look at a graph and you ask how many edges are connected to it, well then if we go one hop or one edge or 1 degree really of separation out from that individual node, we'll come to that node's neighbors. So the number of neighbors that a node has could be one metric of its importance. So G, network X graph objects G have a method called neighbors, and you pass in the node that you want to, and you can pass in the node that you want to have the, for which you want to get back the number of neighbors. And so let me just do this over here. If we do g.neighbors and we pass in node number 7, we get back a list of other nodes that are the neighbors of node number 7. All right? And so we can get the length of that by passing all of that into g.neighbors, into the len function, the built-in len function, and that will give us the integer 7. All right, so with that, you know enough to try the next exercise, which is to create a ranked list of the importances of each individual based on the number of neighbors that they have. Let's see, I think this exercise should take 3 minutes, so we'll time it 3 minutes from now. And I'll give you a few, go ahead, try it out, and I'll just continue talking to give you a few hints. One would be a list of tuples. The other would be, so that's one suggested output where you rank them. So the highest ranked is at the top. So the list of tuples where the first element is the node ID, the second element is the number of neighbors that node has. The other thing that you might want to use is Python's built-in sorted function. And so, yeah, give it a shot. Okay, just want a quick show of thumbs. How many people are done with this exercise? Okay, this one needs a bit more time. And if you're done with it and you want to move on to the next set of exercise, by all means, please feel free to do so. And if you're stuck or need help, actually, this might be a prime opportunity to go talk with your neighbor. Neighbor. Yes, neighbor. Thanks a lot.
Coffee's already outside.
Oh, okay, thanks. Okay, quick show of thumbs. How many people are done? All right. I hear coffee is ready. So what I'll do is I'll quickly talk through my answer for this particular problem, and then we'll take the coffee break. What, 10 minutes, is that right? 10 minutes, is that right? I think 10 minutes for coffee, and we'll do a coffee break, and then we'll come back after that. Okay? So, in the instructor notebook, you'll see there are two possible answers. Really, the goal was to get you familiar with sorting things using the sorted function. And so, g.nodes, so if we use the sorted function, we're essentially sorting some container of things, and it'll return a list. We first pass in the container of things that we want to sort. In this case, we want to sort the nodes, the node list. And then the most important part is we want to sort them by some property, right? So we have a function that computes a value that we sort on. Or otherwise, it'll just sort by whatever its representation is. If it's an integer, it'll sort from 0 to whatever. If it's a string, it'll sort alphabetically. So in this case, we want to sort it not by that, but we want to sort by the number of neighbors it has. We can use a lambda function, which I think refers to an anonymous function, which what we'll do is it'll iterate over every element in g.nodes. We'll call it x. And then we pass in g.neighbors x, and that'll give back a value, which is g.neighbors. And so now the key is to sort by the number of neighbors, and the way we express it is in this line, this little expression over there. And to get it sorted from top to bottom, so most number of neighbors to fewest number of neighbors, we do reverse equals true. Oops, I'll right-click there. We use reverse equals true. An alternative way of doing it is to do the implementation I suggested, which was you use n and g.neighbors of n. So as you iterate over every node inside the graph, and then you pass in you sort by the length of the second element in each two tuple. And again, we pass in reverse equals true. Those are equivalent. Those will give you equivalent orderings, even though the data structure that's returned might not be equivalent. Okay, so at this point, it's a good stopping point to get some coffee. We'll do a 10-minute break. Let's come back at 10:20. All right? I hear the coffee's ready, so let's do that.
Okay, quick show of thumbs. How many people are done with all 3 coding exercises? I think I'm comfortable with this quorum, so let's move on with that. If not, if you're not done, don't worry. The instructor notebooks have all the answers. You can take your time and pace yourself through them as well. Okay, wanted to make a very quick note about degree centrality and its definition. Let's say I have a graph with n nodes, and I want to compute my degree centrality score. If self-loops are not allowed, that is, I'm not allowed to draw an edge from myself to myself, what's the denominator what's the total number of possible edges that I could be connected to? N minus 1. If I'm not mistaken, that's the definition of the degree centrality metric inside network X. That is, so degree centrality is defined as the number of neighbors that I have divided by the total number of possible neighbors that I could have, or the total number of neighbors I could possibly have, sorry. If self-loops are not allowed, then the denominator is n minus 1, and if self-loops are allowed, what's the denominator? It's n, right? So the definition does matter, all right? That's basically the point. So you look at a degree centrality metric that may be implemented in some other library, be sure you double check this little detail before you use it. Otherwise, you might have to do some adjustments if it's not what you're looking out for. Okay, let's try quickly visualizing the network with Circos plot. So there's a keyword called order inside each node, and what I'd like you to do is to color and order the nodes by the value keyed on the order key in the metadata dictionary. The order key essentially describes the order in which the individuals came into the network, and it actually incidentally does also correspond to the node ID that's stored as the node. So on a quick show of thumbs, how many people are done with this one? Okay, we'll wait for a few more. If you're done, you should get a diagram that looks like what I'm showing up there. I don't know what you think, but it looks a bit like the pupil of an eye. Okay, if you're not done, don't worry about it. There's code in the instructor notebooks. I'm going to very quickly talk you through the code. We have the Circos plot object instantiated. In the constructor, we pass in the graph that we're interested in looking at or in plotting. There's a keyword argument node order. So that means it's telling the constructor, I would like to order the nodes by the values keyed on the key order. And then I'd like to color them as well by the values keyed on the key order, right? So we'll get both the ordering and the coloring by the values keyed on the order keyword. You'll get something like this. Let's do a bit of interpretation. What can you deduce about the structure of the network just looking at this guy over here? What are some thoughts that people have the first time they look at it? Back there. Pardon me? Okay, the order is linear. What else do you see? Yep, so there are very few edges that go, say, what is this, pi radians, or 180 degrees from one point to the other. What else do you see? I see some local clusters of connectivity. I don't know if you see that as well. Don't be fooled, it's not by the edges over here, but rather, it's not by the blackness of the edges at the nodes, but rather it's like having multiple strands of hair or multiple cords that arc between sets of nodes. So like this guy over here, it looks like there's a lot of connectivity there. It could have been, say, for example, a tourist group that just happened to all be going through, and two tourist groups encountered one or another, something like that. And then that lady over there correctly pointed out that we've got very few cross connectivity. So people are mostly having face contact with other people that are close in proximity with respect to the order that they came in. It is not ordered by the exact time that they came in, but just the order in which they came in. Okay, I'm hoping that this short example also demonstrates how useful rational visualizations can be rather than big, massive hairballs. Okay, so that's a little bit about node importance as defined by the number of neighbors. We're going to now take a very quick detour and look at paths in a network. And just to give you a flavor of why paths in a network are important, another measure of node importance can be if that node is a bottleneck node in information flow, then you can't take that node away. And we want to somehow figure out a way of quantifying the importance of that node being a bottleneck node. All right? To do that, we'll use what we call graph traversal. And so graph traversal is a common computer science type of exam question and that sort of thing. Now, I don't want to scare people over here. So what I'm giving you is basically the simplest naive version of graph traversal. And there are many ways you could do this, implement a graph traversal algorithm. But I'm just going to show you roughly what it looks like. And so one of the algorithms that we can do is we can do the shortest path algorithm. If I have a network of nodes, what's the shortest path that it takes to get from one node to another? All right? And one way we can approach this is by doing what we call a breadth-first search. Right? So we go like onion layers, essentially. We start from that node, we go 1 degree out. Is my destination node of interest in that first layer? If it's not, we go 2 degrees out. And if it's not, we go 3 degrees out. That's the breadth-first search. Right? And the approach essentially is as such. We have a queue of nodes that is initialized with the start node, and then we start adding the neighbors to that queue, and we iteratively check whether our destination is there. And if it's not, then we'll do some removal and addition operations to that queue, and then check. Then if the destination node is present, then we'll break out of the loop, and if it's not, we continue in the loop until we've traversed all of the nodes in the graph, or all of the nodes that are connectable, rather. And if there's no path that's available, then we should be able to say, oh, there's no path available. So what I'm going to have you do is a bit of practice with algorithmic thinking. And this is a tough exercise. It's 15 minutes long. I'd like you to try to implement a path exists function that follows this specification in the notebooks that you're seeing. It probably should use the breadth-first search approach, and you're free to implement it, the breadth-first search, in any way you're happy to do it, but I've given you skeleton code to try that out as well. All right? If you're done early, you're a genius. Go ahead, move on to the next set of exercises. And if you don't finish this exercise, don't worry. This was not meant to be something where we hit 80% quorum and then we move on. This is an exercise just to get you thinking in terms of graph algorithms, right? And if you don't implement it, it's totally okay. Or you don't finish implementing it, that's totally okay. What matters is that you've tried. For reference, the first implementation that I made had a really fatal bug, and I got caught 2 years ago at a Boston Python rehearsal. And so if you don't get it right the first time around, it's completely normal. I didn't get it right the first time around either. I think I found yet another bug in my implementation. It's a bug in that the q, if len of q evaluates to 0, that should not ever happen in this implementation because I never remove stuff from the queue. So that condition never holds. Back there, yes, comment. If you do a while loop and you pop from the queue, okay, that would work. Yes, that would work. Okay, I've got a note for it for myself, and as is the case with every iteration, I find something that can be improved. So this will get fixed and pushed up to the GitHub repo. You guys will have access to it after the tutorial anyways as well. Okay? But the concept is there. We have a queue. And we keep track of what nodes we visited. And then basically our idea is as we go over every single neighbor, as we go through the queue, we're going layer by layer. We start with this node's neighbors, and then we expand the queue out to its first layer. And then we iterate over each of those nodes, and we ask the neighbors of that neighbor, and we make sure that neighbors of that neighbor, because it includes our starting node as well, we don't want to go back to that node as well. So basically, we keep track of new neighbors or new nodes that are connected, but we have not yet visited. All right, and then we keep on going over for the first layer, and then once we finish that first layer, we'll go to the second layer 2 degrees out and start iterating again. The logic is basically that way. Okay, I made you implement a function and wreck your brain over a function that actually already exists in NetworkX. And this will be the last time that happens in this tutorial. It's the first and the last time that you will implement a function that already exists inside NetworkX. It's hasPath is the function that you can call on. You pass in the you pass in the graph object, and then the ID of the nodes that you want to know whether a path exists between them, and it'll return a Boolean true or false. All right. From this point onwards, anything more complicated, we'll try as much as possible to take advantage of NetworkX functions and compose them together into higher order queries that finds nodes and edges that we're interested in. Okay, so we have shortest path algorithms, we have a hasPath algorithm, and it's predicated on finding the shortest path between two particular nodes. So, for example, if you go down here and you run this guy, this function nx.shortestPathG, and you pass in the two nodes for which you want to know what the exact set of nodes are that are involved in that shortest path, it will give you that. It'll return you 4, then 90, then 111, then 112, and so on, all the way until you get to 400. And so, incidentally, if you inspect it on other graphs, it actually is that order as well. It's not just some mishmash. It starts at 4. You go through, the next node you'll find is 90, and then the next node you'll find is 111, and so on until you hit 400. Note, though, that if there are multiple shortest paths between a pair of nodes, NetworkX will only give you one of them, right? It'll only give you one of them. Okay, so what I'd like you to try now is a bit of this visualization. Earlier on that I had mentioned to you that nx.draw is probably good for like small subsets of nodes that exist in a bigger graph, and nx.draw is actually good for this particular use case where you draw, say, a path between two nodes. So what I'd like you to try is to try this particular exercise. It extracts the edges in the shortest path, puts them into a new graph, and draws that new graph to screen. So give that a shot, and then give that a shot, and then let's see how that goes. 10 minutes for this exercise. But if you need less than that, that's cool as well. This is basically practice with composing functions from NetworkX. Quick check, how many people are done? Oh, wow. We don't need 10 minutes for this, potentially. All right. We'll stop at 10:05, move on from there. If you're not done again, don't worry. Instructor Notebook has a possible implementation. And if you're done and you want to move on to the next set, skip the challenge exercises below. If you want to skip right to the bottom of the notebook, that's totally cool as well. this one can be changed. Okay, so with that, we're going to end the hubs and paths notebook. Main takeaway points, there are two metrics of node importance, degree centrality and betweenness centrality. They have their own definitions. They're alternate views of how a node can be important inside a network, right? We're now going to move on to cliques and triangles. So I'd like everybody to open up notebook number 4 now. Run that first cell and load the data as usual. All right, so this is a small sort of network. There are physicians that were queried back in 1966, so this is like a very old data set. It's older than I am. There are 246 physicians in 4 towns, and a node represents a physician, and an edge between 2 physicians indicates that the left physician would look to the right physician if the right physician is his friend, or that he turns to that other physician for advice or is interested in a discussion, right? So it's sort of a trust network as measured by these 3 criteria. There's always only one edge between 2 nodes, even if more than one of the listed conditions is true, right? So as long as any one of those 3 conditions is true, in some way, physician A trusts physician B by that criteria, we'll just draw a line. This is supposed to be a directed network in memory, but I'm going to intentionally load it as an undirected graph so that we can have a flavor of some of the interesting things that show up when we talk about graph structures. So load this cell over here and very quickly draw a Circos plot of the graph, a plain vanilla one. If you haven't done that, run that cell. And I want you to take a look at that one for a little bit and tell me what you see over there. Okay, which group is that? The bottom half. Okay, what else is there? It looks like the bottom half is communicating only with the bottom half. What else is there? Sorry? As well, okay. It looks like there might be 3 distinct clusters as well over there. Okay, anything else? Okay, I basically see the same thing there. And so on that point, that there seems to be 4 distinct clusters, which might particularly map to the 4 towns. Given that this was 1966, it sort of makes sense. Given that there are 4 distinct clusters there, we'll be able to find graph theoretic metrics that help us test and visualize whether that's actually true. That'll be in the bottom. Okay, let's talk about this topic called cliques. How many of you have been in a clique? I've been in one myself. It's no shame in that. But what's the definition of a clique? Have you ever thought about that? Same ideas, okay. What else? Pardon me? A network cluster of some sorts, exactly. Okay, connected subgraph of some sort. Okay, in a social network, we might think of cliques as groups of people in which everybody knows everybody. So in this case here, we're not a clique because not everybody knows everybody. But say I go out with a whole bunch of Boston Pythonistas, we've already met up with each other at the Boston Python meetups, then we are a clique in the whole PyCon community, right? Because we all know one another already. So what is then the simplest clique that you can think of? Pardon me? A family. Let's go graph theoretic, actually. Sorry. What's the simplest clique? Exactly. The simplest clique is 2 nodes in an undirected graph, 2 nodes connected by an edge. So what's then the simplest complex clique? Three nodes, basically. Just add 1. All right. So triangles. Triangles are the simplest complex clique that you can look for inside a network. And if you think about it, every higher order clique can be decomposed to a set of triangles. Well, it can also be decomposed to a set of edges, but triangles are the more interesting structure, right? So you can decompose like a 4 clique in which you have 4 people, they're all connected, fully connected to one another. You can decompose that into its component triangles. And so that's a very interesting thing to look for. So a way of looking for triangles is to iterate over, a way to look for triangles in a graph is to iterate over every node and look at its neighbors and ask, do my neighbors also have an edge to one another? And if that's true, then I'm in a triangle relationship with my two other neighbors there. All right. So over here you can see some example code. It's also should be in your notebooks, the student version of the notebooks. You see that's basically the kind of logic that you would go through to look for that. Now, NetworkX already has a function that counts the number of triangles that a node is present in. So actually, technically speaking, you don't have to implement an isInTriangle function. You can get the result from nx.triangles. If it's 0, it's false, and if it's more than 0, it's true. All right? So there's that function over there. So what I'd like you to do is try the next exercise over here. So now it's not a matter of finding out whether a particular node is present inside a triangle relationship or not, but to find every triplet of nodes that are present inside a triangle relationship. So that's the exercise for you. Let's try, oh sorry, not the triplets, but the set or the list of nodes that are involved in a particular triangle relationship with a given node. So try that exercise. We'll take 5 minutes on it, and then we'll check back here at about 11:25. Thanks a lot, Tom. Yes, please. A hint here is you'd want to use the itertools combinations function, which lets you iterate over every 2 combinations or 3 combinations or 4 combinations of nodes. In this case, you only want the pairs, so every combinations, you pass in the parameter 2 inside there. And all you have to do is ask whether an edge exists, and we've shown you the function call already. It has edge. So little hints there.
Near to like what? 412. Then I'm off.
Okay, got it.
Yeah, because then I'm manning the registration.
Okay,
Right.
all right, thanks. Okay, quick show of thumbs. How many people are done with this one? All right, we'll wait for more people to finish. And if you're done, feel free to move on. The next exercise is on open triangles. So a slight modification to your previous code will get you up there, get you to that answer. All right, it's 24. So I'm going to very quickly talk you through the logic. This will help you prepare for the next set of exercises on open triangles. So the idea here is I initialize my, so I have a function whose signature is get triangles, and I pass in g and a single node for which I'm interested in finding out the neighbors of that node. So first off, I get the neighbors. Then I initialize, because I'm interested in getting that node plus all of the other nodes that are involved in a triangle relationship with it, I initialize that set with the node of interest first. Then after that, I iterate over every single pair of neighbors inside that list of neighbors, right? And then I ask, is there an edge between neighbor 1 and neighbor 2 for every single pair of neighbors? And if there is, then I'll add those two nodes to the set. And because it's a set, it won't repeat. And I return at the end the set of nodes. And so I can get that over here and then draw the subgraph to screen, and it'll look something like what's shown on the screen. All right? And you can actually verify that we've only drawn the triangle relationship neighbors and not the entire set of neighbors by drawing that node plus all of its neighbors and verifying that, yeah, we've only captured the triangles that are involved there. Okay. Triangles are interesting because they're the simplest complex clique in a graph. So I don't know if you've heard about this, but LinkedIn about, was it 2009 or 2008 when they were trying to build up people's social network, help people build the graph representation inside their database of people's professional networks. They actually came up with this, they stumbled on the insight that was, if I know A and I know B, but if I know A and I know B, then there's probably a chance that A also knows B as well, right? And so what we call this is triangle closures, or triadic closures, I think is the technical term out there. So finding triangles is important, but finding open triangles could actually end up having good business applications downstream. So what I'm going to have you try is take the same logic as you've seen above and try to do finding open triangles, right? Where for a given node, we ask, are my neighbors connected or not? And if not, then maybe there's something that we can do to connect those two together. All right, so some people are pedantic and they'll say, open triangles, don't you mean just a line? Like A, B, C, right? It's sort of the same thing. Graph theoretically, or from a topology perspective, they're essentially identical. So can you write a function that identifies for a given node other two nodes that it's involved with in an open triangle? And in this case, note there are two scenarios that you have to consider. There's one scenario where the node that we're interested in is the middle node, and we only want to look at the two neighbors on the side. But there's also the scenario where the node that we're interested in is the termini node of the line or the open triangle. And so we have to go ask if the neighbor of my neighbor is also my neighbor or not. All right? So but we're only going to consider that first case where we're talking about that node being the middle node. All right? So go try that out. this one should be a fairly quick implementation of that is very related and similar to the one that you had above. All right, quick show of thumbs. How many people are done with this one? All right, we'll give just 2 more minutes for this exercise. As a hint for those who are still working on it, it should be fairly similar to the previous exercise with the switch of a single conditional. And if you're done with this one, feel free to go to the find cliques of size n exercise below as well. All right, so we're at 11:30, so I'll very quickly talk you through the only change that's required, or the most crucial change, sorry, that's required if we want to find open triangles where the node of interest is the middle node. Then we only have to do change if g dot has edge to if not g dot has edge. And then we'll be able to get the set of nodes that it's in an open triangle relationship with. Okay. So triangle closure, like I mentioned, is one of the foundational ideas behind, say, closing behind friend recommendation systems or other recommendation systems. And so naturally, it's going to be much more complicated than what we've shown here, but this is sort of the basic idea there. So next thing is we're going to talk about cliques and find cliques of a size n, of a given size n. And so NX, network X implements a find cliques function that will find every 2 clique and higher that exists in a graph G. All right. So if you do nx.findCliques, let me just actually do this. nx.findCliques, it gives you a generator object, and so that's why we have to cast it as a list to get back every 2 clique or 3 clique or 4 clique or n clique that exists inside there. All right, so this next exercise is simply practice composing functions again. So we'll want to find maximal cliques of some particular size. So give that a shot, 3 minutes, and we'll come back after that. Yes.
Is that like where all the nodes know each other, or?
Yes, so the definition of a maximal clique is this. For that set of nodes, I cannot add in any more nodes and still be a clique. So if I add one more node to that set of nodes,
Yeah.
then the new set of nodes is no longer a clique.
Okay.
Right.
Because there's at least one person that doesn't know that added node.
That's right.
Got it.
That's right.
Okay.
So this is the definition of maximal clique. What's your name again? Dylan.
Yeah.
Okay, got it. Okay, so Dylan asked the question just now at the front, and the question was, what exactly is a maximal clique? And I think it's an important point to highlight that I've missed out just now. So a maximal clique is defined as such. If I have a set of nodes, and those set of nodes form a clique in the graph, a maximal clique is such that that thing is a maximal clique if and only if I cannot add another node and still have that new set of nodes be a clique. Right? So if I add a new person into the group, so I'm Boston Python, I'm from Boston, so the Boston area, having studied there. So Boston Python is my clique. We are a maximal clique if someone from Portland Python comes in and and we're still not a clique, including the Portland Python person, right? So if I added the Portland Python person in, we're no longer a clique at all. And so based on that definition, the Boston Python set of nodes is a maximal clique, right? If I could add Portland Python in and we'd all know each other still, then that Boston Python set is no longer a maximal clique. We would be a maximal clique if and only if I add another node and then we're no longer a clique. All right? That's the definition of a maximal clique. So the maximal clique of size n is something like that. I only want to highlight two things here, which are my defensive programming checks. If you're developing a function that acts on data, you might want to include some of these assertion statements that explicitly encode assumptions you're making about that function. It's just good practice. Okay. Cliques are a type of connected component, right? They are a maximally connected component. That means everybody knows everybody. But we can also generalize this idea of connected components to non-maximal cases. So in the case where, you know, a path exists between every pair of nodes inside a graph. You can have disconnected graphs, by the way, and that's sort of the observation everybody made at the beginning, where it looked like there were 4 disconnected subgraphs in this bigger graph. So connected components, there's a definition that's from Wikipedia over there, and NetworkX implements a function that lets us find all of the connected component subgraphs inside there. So we had a hypothesis that there might be 4 connected component subgraphs in this Physician Trust network. Let's see whether that's true. If we use the nx.connectedComponent, we use the nx.connectedComponent subgraphs function, and we pass G inside there and then cast the whole thing as a list because it's a generator that's returned, we'll notice that there are actually 4 connected component subgraphs in there, and it looks like our visual intuition was correct. So then, based on this, I would like you to try doing something a little more fancy now. So let's draw a circles plot of the graph, but now let's color and order the nodes by their connected component subgraph, or group them, by their connected component subgraph. And what you're going to have to do in this case is somehow annotate in the metadata dictionary what connected component subgraph it belongs to. And you can choose an arbitrary label for that. So you can be connected component subgraph 0, 1, 2, 3, could be A, B, C, D, your call. You just have to put that metadata inside each node. like I was mentioning, you can talk with the neighbors.
Unrelated to this, but so if I had a graph with a bunch of, let's say, disconnected subgraphs,
Mm-hmm.
or realistic graph,
Yeah.
I wanted to find in each subgraph the node that, if I were to connect it to the other subgraphs, would be the most efficient way of uniting them all. I'm assuming I would write some algorithm that would do a maximal click for each one to break them, or identify the fully connected subgraphs, and then I'd run the betweenness within the
Hold on,
subgraph.
hold on. What I don't get is, what do you mean by connect the connected component subgraphs most
Connect the disconnect. Oh, and then what's the
most efficiently? Because technically speaking, you can take any node.
yeah, that's true. I guess I should
Yeah.
be more specific there. I guess I mean the one that would maintain the shortest, I don't say shortest distance. Yeah, I see what you mean.
Yeah. So okay. So but I guess yeah. The key there is then what's the metric by most efficient?
Fair.
Yeah.
That's fair. Okay. But that's generally the way you could approach that.
Yeah.
Okay.
Yeah. That's right. So I think the brute force way would be take every pair of nodes from each of the one node from one subgraph, one node from another subgraph, brute force search over all of them, and compute for that given pair if I connect it, is my efficiency metric satisfied or maximized or yeah. All right, how many people are done with this one? Show a thumbs. We'll give a bit of time for other people. If you're stuck with it, I don't want you to be too stuck. So go ahead, feel free to take a look at the instructor notebook. Note that you can enumerate over the subgraphs, so you may want to try that. And even though you've got each individual subgraph as a little graph object in memory, you can use that enumerate label to annotate the node in the big subgraph, right? So you can do that. Totally valid. Big graph, sorry, big graph. All right, we're at 11:41, and in the interest of time, I'm going to very quickly talk you through the solution. This is something that, by the way, beyond just this particular use case, it's sort of a generally useful thing to be able to do, which is you have some alternate representation of the graph, but you want to annotate the original graph based on this alternate representation. All right, so in this case here, the alternate representation is that we've already got the 4 individual subgraphs. They exist in memory as 4 individual graph objects themselves. All right, so I can, and they're all collated together in this container called CC subgraphs. So if I iterate over each of the subgraphs, I might want to use, say, for example, little lowercase g as the loop variable for each graph in CC subgraphs. But then at the same time, I'm trying to look for a unique identifier for each subgraph, and so I add in the enumerate function and add in the I for the index of my subgraph. And so the enumerate function will give me 0, comma, graph object 1, graph object 0, sorry, 1, comma, graph object 1, 2, comma, graph object 2, etc. The next thing I want to do is, because the node set in subgraph little g is a subset of the nodes in big graph G, big G, I can iterate over every single node n in the smaller subgraph, and because it corresponds to the same exact node in the original big G graph, I can annotate that big G graph with the node I can annotate that node with a subgraph ID, which corresponds to I, which is the enumerate loop variable for that particular subgraph. So I start with subgraph 0, iterate over every node in subgraph 0, and label them in the big graph as, oh, I belong to subgraph 0. Then I go to subgraph 1, and I go to label every single node there, and so on for every single subgraph inside that list of subgraphs. And so when I plot that, I'll get something that looks like that. The API calls are up here. You can see them in the instructor notebooks. And indeed, there are visually what we had before, what we thought before, where there's 4 disconnected subgraphs inside there. It's confirmed by the use of the connected component subgraphs, and we can visualize that with a Circos plot, right? Okay, meanwhile, admire and perhaps also fear for this country as the division of Congress gets worse and worse and worse and worse over the years. And what we're hoping to see is not that there becomes 2 connected component subgraphs in the US Congress. All right, so that would be a total disaster for democracy and the likes. So let's just hope that that scenario does not happen. Okay, all right. How are people feeling right now? Brain fried already? Up for more? Want to get a sense for you. If you're feeling good right now, give me a thumbs up. If you're feeling okay, give me a horizontal thumbs. If you're feeling really tired and brain fried, give me a thumbs down. Oh, that's good. Okay, thanks for thanks for no thumbs down there. What's going to come up next is fairly light, not very much in the way of intellectual stuff, so conceptual stuff. The toughest part is already over. The next part is just going to be some practical things about how do you load data and how do you represent data in, how do you represent other types of graphs in Network X, all right? I'd like you to open up notebook number 5. There should be Graph.io, a student version, if I'm not mistaken. Yes, there is. So open up that one. And the main purpose of this notebook is essentially to give you some code examples of how you take node lists and edge lists, which may be represented as CSV files, and convert them into NetworkX graphs in memory. When I took a look at the NetworkX API, I think there's this thing called from pandas and to pandas. It wraps a lot of, I think under the hood, it basically wraps a lot of stuff that we might be coding manually over here. But knowing how to do this on your own gives you a lot of flexibility that maybe read pandas and the likes might not give you. All right? Okay, so recall when I mentioned at the beginning of the tutorial, a graph can be represented as 2 sets, a node list and an edge list. If I have node lists, nodes that have metadata, then I can actually represent that entire thing, that node list, as a table, a CSV file, right? In which I have a column that says, here's my node ID, blah, 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 and then here's all the metadata that I want to turn into a dictionary later on, right? Blah, 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 blah. Okay, so likewise, we can do that for the edge lists, where we have node 1, node 2 involved in an edge, and then the rest of the columns represent the metadata that describes that particular edge. All right? So like I was saying in the social network, the date on which a friendship was forged could be the metadata piece that's added in. So we can use CSV files to store network data. And CSV files, so the Divi bike sharing data set that you're going to load is one example of this. So I'd like you to run this first cell over here. And this will tell you whether, I didn't provide this in the instructions, but you do need to unzip the Divi 2013 data set that's inside the datasets directory of the GitHub repository. So run that cell and check to see if Divi 2013 is already present. If it's not, I'd like you to unzip that file, and then we'll be able to run the cells below. I'll give you a quick minute to get that done. When you're done with that, run the next cell, which is the read CSV, which reads the CSV file into a pandas data frame. So first off, I'm going to very quickly describe the data. It's essentially bike sharing trip records from station to station, right? So what would be the most natural thing that's a node in this graph? The bike stations. And what are the edges? Rides that start at one station and end at another station. And this would be most naturally represented as a directed or undirected? Directed. Okay, good. We're on the same page. So if we have the stations thing stations CSV file read into memory. Oh, just a quick check. How many people are able to read this into memory? Thumbs up. Okay, good. Reading this into memory, we get the node list. And so you can imagine, you can either use ID or name as the node. If you choose to use ID as the node, it's a more compact representation. If you choose to use the name as the node, it's a more informative representation, just less compact, right? You do what floats your boat. The metadata can then be the latitude, longitude, the capacity, landmark IDs that are next to it, and the date that it came online, for example, right? So we can do the metadata in that way. How would we do this? Let's see. I have something wrong over here. Oh, sort. Yes, that's right. This is the old API. So if you run the next cell, you can open up the trips dictionary. Oh, I need a key for this. Sort index? Okay, let's just do sort index. Thanks for the catch. There we go. So we have every edge that's represented inside here, and we have a lot of metadata that's included. Start time, stop time, the bike that was used, the trip duration, where it came from, where it ended, and all that stuff. So the goal here would be, how do we convert the stations CSV file into node lists and the trips CSV file into edge lists, and how do we add that into the NetworkX graph? So there are ways that you can do it. Let's start first with the node and the node attributes. One thing that you can do is you can do something like this, where you initialize the graph G and then iterate over every single row inside the pandas data frame, and that's the code for it. The idea here is we can, because if we do r comma d in stations.iterRows, well, what it'll do is it'll use the index as the r variable and the rest of the metadata, rest of the data as the d value, and we can then add this particular node r with the attribute dictionary d, but that's a row from a pandas data frame, so we can convert that to a dictionary, and that will give us the representation that's needed to add nodes into the graph. All right? Likewise, we can look at adding in the edges. Now, if you run this block of commented code, you run the risk of waiting to the end of the tutorial and it'll still not be finished running. We're not going to add the edges that way, where we go one by one and increment them. We're going to take a bit of a pandas shortcut. This does require a bit of pandas mastery for you to know how to do this, and so treat this as a, here's how we do it, and if I don't know how to do it right now, I'll go and learn a bit of pandas so that I understand what's going on. But otherwise, you can just use this over here. The reason we do this is because there are multiple trips that are possible between pairs of stations, but we're only interested in, say, the number of trips that go over there, that go between pairs of stations. So what we can do is we can iterate over the trips data, group it by from and to station ID, and that will create sort of an index-like thing that will be our start and stop. And then the rest of the data is data frame-ish, so it's got a number of rows because it's been grouped by pairs of start and stops. So for a particular start and stop station, it's got this amount of data from another one that's rarely for where trips are rarely taken, it might have a shorter thing. And so the count keyword is our metadata that we're adding in, and it's simply the length of how many records fall under that particular group of start and stop stations. All right? People sort of clear with that? That's basically the logic behind this. And even that takes a little bit of time. Okay, so with this next set of exercises here, I'd like you to take a little bit of time to iterate over the graph object. So if you should have been able to run all of those cells in turn, and now have a graph object in memory. So I'd like you to exercise your memory muscles a little bit, make a scatter plot of the distribution of the number of edges that have a certain number of trips. So most edges, so if we have a high towards 0 and the long tail distribution, for example, most trips. Most edges will have few trips, and then few edges might have long trips, or it might be the other way around. What I want you to be able to plot that. The x-axis is number of trips, and the y-axis is the number of edges that encode that number of trips. That's right. Quick check, how many people are done with this exercise? Thumbs up. All right, we'll give some time for more people to finish. We'll probably go through this at 12 p.m. We'll give 4 more minutes for people. If you're done with this one, I'd like you to skip down to the last portion, and so that you just have a bit of information about how you can read and write binary files, and that's good enough for in the interest of time. The rest of the exercises here are sort of plotting exercises. And if you're done, you should get something that looks sort of like this guy over here. All right. How many people are done here now with this gun? Okay. If you're stuck with getting the distribution of stuff, you can take a look at the instructor version of the notebook. Essentially, we want to get the count, which is the count value encoded on each edge, and we want to count. We're counting how many times each count value shows up. It's like this count the number of counts. So 29 might show up 13 times. 1 might show out 1,500 times. That's the sort of idea here. Okay? If you get something like this, then you've done it right. The reason I wanted to show you this plot is because this is a characteristic type of distribution plot that someone might make when describing a network. All right? So we'll say on the x-axis, it's the number of trips. So this might be, for example, the weight distribution on the edges. All right? So the number of trips might be considered the weight of that edge, indicating how important this path from this node to that node is. The way you interpret it is essentially as such. If you look at the bottom right-hand corner, you'll see some nodes have approximately-ish 2,000 number of trips recorded between them. And the number of nodes that have that is essentially just 1, right? So one node has this particular number of trips indicated. One node has this number of trips indicated. Then we go up to some nodes that have about some values of number of trips for which there are about 10 nodes that have this value indicated, right? And so that's how we interpret this distribution plot. Okay, so that was just a little bit of an exercise, get you familiar with that. The main idea from this notebook really is, though, I have CSV files, and if I take my knowledge of, say, pandas to manipulate the CSV file in such a way that we structure it as my index being the nodes, and so for the node list, my index is the nodes, and the rest of my columns are my metadata, then I can use the two-dictionary format or the two-dictionary method for a pandas data frame or pandas record, basically, and convert that into a dictionary format that can then be passed in to the NetworkX API. All right, that's just the big idea there. Now, sometimes, if you scroll down to the bottom, sometimes, as is the case that I encountered with my own thesis work, I'll be working with a graph in one notebook, I'll create it, but then I want to keep that notebook self-contained, and it's sort of like, here's how I created the graph, and here's all the steps detailed. And I want to keep another notebook that says, here's how I do the analysis on this graph that I created. I need a way to pass the graph object from one notebook to the other. One way to do it is to pickle it to the disk, to your hard disk, and then load that pickle in the next notebook. So there are two functions to know. One is write gpickle. You pass in the G object, the graph object G, and the handle, so the file path that you want to save it as. And that will save it to disk. And then to load it from disk, use this syntax over here, nx.read gpickle. Right? So that'll load that from that graph from disk. It can be useful in scenarios that I described just now. So I do analysis, graph construction in one notebook. I want to do analysis in another. It can be useful in another case where I basically want to be able to. I've created all of these graphs, lots and lots and lots and lots and lots of graphs, and I want to iterate over them on disk, right? So I've done this thing where for research, I created a lot of very similar looking graphs, and then I wanted to look at graph differences between them. And so this was another scenario where pickling them on disk was better because then I wouldn't have to run into memory issues holding all of these many, many graphs in memory. Right? I could just read them from disk when needed and then discard it when I didn't. All right, so that's notebook number 5 in a nutshell. Basically, two big ideas: CSV files, two graphs, to a graph object. And then the other one is I've got a graph object and I want to move it between notebooks. Let's use the pickle function. All right, we're near the end. I want to give everybody a very quick tour through bipartite graphs. And I think this is sort of useful in a different way as well. So let's open up notebook number 6. So first, I want to tell you what a bipartite graph is. All this while, we've been working with unipartite graphs. And a unipartite graph does not have nodes that are explicitly partitioned into multiple sets. A bipartite graph takes that node set and says, okay, I think this set of nodes belong together, and this set of nodes belong together, and logically, there should not be any edges between nodes within one set. That means I can only have edges across sets, but not within a set. What's an example of this? An example of this might be a customer product purchase record, where I have customers as my nodes, as well as products as my nodes, and I want to indicate that a customer purchased a product using an edge. So logically speaking, I cannot have customers purchase one another. And logically, I also cannot have products purchasing one another. And so in this graph definition, an edge can only exist between a customer and a product and never within each of the node sets. And this is the definition of a bipartite. This is an example of a bipartite graph, right? Visually, it's often represented as you'll see in that big diagram in your notebook. So we have a crime data set. I don't want to go too much into the details of what this crime data set is all about, but it's basically I have crime events and I have people involved in that events, whether they are a suspect, a witness, or whatever, or something else. We want to know whether, and we want to know what the relationships, we may be interested in the relationships between people based on their involvement in certain crime events, so that sort of stuff. And so this will introduce to you a few interesting new concepts over here that, well, I don't want to burden you with the code, but I'll just sort of introduce you to what those new concepts are. So the first concept that I want you to, so if you could run the next few cells below there just to get the graph into memory and so you can preview what the data sort of looks like. The first concept I want to introduce to you is this idea of projections. And so projections are essentially the connectivity of one set of nodes conditioned on their connectivity to the other set of nodes. All right? So for example, let's go back again to the customer product thing. Customers A and B both purchased product 2. Let's say we had those two edges recorded in there. If we wanted to get the customer projection, we would say customer A and B are connected to one another because in the bipartite graph, we can draw a path from customer A to B through product 2. All right, so that's a projection from two partitions down onto one partition. And A and B are connected because they're connected through product 2. All right, so that's the idea here. That's the concept of a projection. Network X has a bipartite module, so nx.bipartite, and underneath that you have all sorts of functions inside there. In the interest of time, I'm going to convert this notebook from exercises to more lecture style, so you can follow along on the instructor notebook instead of trying to attempt the exercises. But it'll give you a flavor of what's going on. So I can use the bipartite module's projected graph function. Oh, sorry, I'll give everybody 10 seconds, 20 seconds to open up the instructor version and scroll down so you can see what I'm highlighting over here as well. Let me also just take out the header and take out the toolbar. Okay. If you scroll down a little bit just past the first exercise, you'll see what I'm looking at. We have the projection. The projected graph function takes in a graph G and a set of nodes that belong to the partition that we want to take a look at. So in this case, we have the person and the crime nodes. And let's say I wanted to know the relationship of the people involved, conditioned on their involvement with the set of crimes that are out there. I can get then this bipartite projection called PG, which only contains person nodes and does not contain crime nodes. It'll have all of the edges conditioned on their connections to crime. Then again, we can also visualize the person-person crime network by looking at it from the lens of a circles plot. And because, again, the metadata that's stored on this graph, there's male and female participants inside the crime, we can then visualize their connectivity in this fashion. I'm not going to belabor this figure too much, but just know that we can get the projection. It's a graph object in its own right, and that means we can pass that into the circles plot constructor methods and use that to make these plots. Likewise for the other partition, so we had the person partition, it logically had two, based on the data, it logically had two ways of grouping the nodes underneath that. In the crime partition, there's no logical way of grouping, or at least on the metadata, there's no logical way of encoding it, so then we just simply encode it by its, order it by its connectivity and color it by its connectivity as well, right? And so we can get a circles plot that looks like that. And note, those two plots were just projections. They were not the original, right? They were not the original. This is just the crime subset of nodes or the people subset of nodes. On this point of degree centrality, do you remember when I said degree centrality what the definition was? It's the number of nodes I'm connected to divided by total number of nodes I could possibly be connected to. So in the bipartite graph definition, what changes? The total number of nodes I could possibly be connected to. Because I can only be, in the bipartite definition, I can only be connected to nodes on the opposite partition. I cannot be connected to nodes in the same partition. Therefore, my denominator changes. The total number of nodes I could possibly be connected to changes. And therefore, I have a different metric. The formula is the same. The denominator is what changes, okay? So you'll notice the degree centrality metric will change depending on whether you use the bipartite metric or the regular metric. Now, note that in memory, these network X graphs don't, in memory, they're actually just using regular graph objects. So technically, you can compute the vanilla degree centrality metric for these graphs, but it wouldn't make any sense because they're bipartite graphs. So you really want to use the bipartite module, right? In addition to that, graphs have a natural matrix representation. If you go back to that first matrix plot that I showed you, with bipartite graphs, they also have a natural matrix representation. The rows can be nodes from one partition, and the edges, the nodes from the other partition, right? And with that, then we have what may not necessarily be a square matrix. It'd be more likely to be a rectangular matrix. And we can do some fancy things over here. I'm going to leave this as, I've told you about it. You can go back and think about it more. But essentially, it's as such. Let's say we have a matrix that looks something like this guy over here. There are customers as rows and products as columns. 3 customers, 4 products. If I take the transpose of the matrix, I can matrix multiply the customer product bipartite graph against its transpose and get back the customer projection in matrix form. It's really elegant. If you take a look at it, the connectivity matrix is represented in the off diagonals. So that's in this matrix over here, that's the 0, the second and third element in the first row. Well, basically the off diagonal elements. And the diagonal elements indicate the original degree, the number of things that it was connected to in the original graph, right? So customer 1 made 1 purchase. Customer 2 made 2 purchases. Customer 3 made 3 purchases. And if you look at it back here, it's exactly that. Customer 1 made 1 purchase. Customer 2 made 2 purchases. And customer 3 made 3 purchases. So this matrix representation is really, really elegant. And in addition to that, we can compute, so beyond that, we have the bi-adjacency matrix. So you can take a bipartite graph in memory and compute the matrix form. Network X provides the functions to do the conversion. And from that, let's say you have a really large graph and the network X functions are taking too long to compute, you might be able to speed things up using the matrix multiplication operators instead. And this is where I'd encourage you to get Python 3.5 or higher, because Python 3.5 has this @ symbol that lets you do this matrix multiplication step. So this is the matrix multiplication of the crime nodes against, so what we want to get is the crime nodes projection, right? And so if I do it with matrix multiplication, it's about, 428 microseconds per loop. And that's about 30 times faster than the projected graph function, which basically operates on Python data structures. Now, there's a trade-off here. If you use the matrix representation, you lose a lot of metadata, right? You basically just have numbers. You don't have the rich metadata that's encoded. So you want to do some other metadata meta-analysis on the projection, you're going to have to use the projected graph function. But if you're only interested in the structure of the connectivity and that other metadata doesn't really matter, by all means, go ahead and use the matrix multiplication. Okay. All right, I'm going to stop that. I'm going to stop it over here. If you go back and look below, there are 2 sets of bonus notebooks. And these bonus notebooks are, one is on statistical inference on graphs. Now, I've found it's always been a challenge to do the statistical inference portion in a live tutorial, so I've designed this instead as something you might be able to self-pace at home. The reason is twofold. One, every time I get into this, I get into philosophical statistical fights with people, and so I want to completely avoid that in a live tutorial setting. And number 2, it also is predicated on being able to understanding things like bootstrap resampling, simulations, creating simulated data and that sort of stuff. And sometimes it's not the case that a large fraction of the tutorial participants don't have that background. And so I'm going to leave this as bonus material you can take home. Now, if you finish that notebook and you finish all of the plotting exercises, the Circos plotting exercises inside the other notebooks over here, then there's bonus notebook number 2, which does a little cute thing that I was trying to teach myself how hashes work. And so if you do this, if you open up notebook number 2, it'll iterate through all of the Circos plots that you've made. And if you pass in your name, it'll compute a hash that is the order of a potentially unique order of these Circos plots, and it'll produce one summary plot for you at the end. So if you go back and finish all of that, bonus notebook number 2 is there for you to produce an ordering of the Circos plots that is essentially a hash of your name, right? So that's a little thing that I wanted to leave with you. At this point, are there any questions about the material in general so far? If not, I'm happy to chat after today, by email, whatever. Happy to receive critique and comments on that. Oh, by the way, yes, in terms of critiques and comments, I would like everybody to do 2 surveys, please. So the first one is the PyCon tutorial feedback. And then the second one, so I have it as a shoutkey URL, shoutkey.com/keep. Shoutkey.com/keep, and that will bring you to the right URL. And if it's not the case, let me know, and I will. Oh, it's not active. No way. I thought I did that. Okay. All right. Never mind. I'll have you do the feedback that I will use personally. If you can open up the README Markdown file. Scroll to the bottom. The URL is URL number 7 at the bottom of the README file. Or if you go to the feedback section, you can click on the link on GitHub, feedback, and fill in that survey. Please do that one. That one's a short one. 3 minutes, 5 minutes, I think you should be done. And then I'm going to create the shout key for the PyCon feedback. Okay, so for your information, it's now, the PyCon tutorial feedback is shoutkey.com/lime. As in key lime pie. All right, if you're done, thank you very much. Lunch will be in the Oregon Ballroom, which is upstairs. It's this big ballroom. I did have instructions to let people know if you've requested a kosher meal, let a server know. And there are buffet stations for vegan, vegetarian, a separate buffet station for vegan, vegetarian, gluten-free, and halal meals. All right? So thanks for coming. I hope you all had a lot of fun with the programming exercises in this tutorial, and hope to see you all around PyCon. Okay, let's get started. My name is Eric, and I'm a freshly defended grad student. I just finished my doctoral training, and it's a real thrill to be here to share with you some of the knowledge that I've gained over the past few years in network analysis and the likes. It's a topic that's close to my heart, and particularly because it's a tool that's been useful for my dissertation research. So before we launch into the actual material, I want to get people warmed up, and so let's try this little short quiz here. There's a list comprehension on the screen, and if you open up Notebook 1, you'll be able to see that as well. My question to you is, if I have this list comprehension, as shown over there, there are two variables for which I'd like to know what your thoughts are on a plausible data structure for those variables. They are S and my favorite things. So what could they be? Popcorn style, feel free to raise your hand. So dictionary for S and list for my favorite things. That's right. Are there any other plausible data structures? Pardon me? All right, so anything that behaves like it's got a selector.
syntax, right? So you can select into a key of some particular thing. So dictionaries, plain dictionaries are one, ordered dictionaries are another. I'm not sure if named tuples are allowed. I think they are allowed. You're allowed to use the selector syntax on that guy as well. Okay, corrected. And the reason is because the moment we connect, we're automatically bidirectional friends. What a technical term, bidirectional friends. What about Twitter? Twitter's directed because it's based on a following relationship. So you have unidirectional friends. You don't have bidirectional friendships. Yeah, all right. And then air traffic networks are an example of another directed network as well. Okay, so from this tutorial, it's my hope that you'll be able to do a few things in practical terms. So the first one is use NetworkX. This tutorial material is both conceptual and practical, and at the practical level, I've chosen NetworkX because it's a library that provides a simple API for the manipulation analysis of graphs. There are other graph libraries out there. I'm not going to go into them today, but you can do your own exploration. My hope is you'll be able to use NetworkX in the Jupyter environment to do network analysis problems. The second one is I'm hoping you'll be able to be convinced of the utility of not visualizing networks with hairballs. Right? I do not like hairballs as network visualizations, and I'm hoping to convince you of that as well. So there are rational visualization methods, for example, circos plots, hive plots, etc. I want you to be able to have some tools at hand to be able to do that. The third one would be to think through network algorithms. Right? So you don't have to, at the end of the tutorial, be like the most efficient algorithm writer, but I do want you to be able to think through network problems in an algorithmic sense, and we'll get a flavor for that. There's one particularly hard exercise in the middle of the tutorial which has caused many, many tutorial participants before lots of headaches during the tutorial, but a bit of coffee at the end will solve that for you as well. It's my hope that you will be able to think through network problems through this tutorial, all right? And the final one would be thinking through statistics that describe a network, right? So, the degree centrality distribution as a teaser is one thing. What's the distribution of connectivity? Getting the edge list. So previously, g.nodes gives us the node list, and we can get the edge list by doing g.edges. And may I ask now, what's the data structure represented here? A list of what tuples? 2 tuples. It's important. The tuples are specified by a size as well, right? So they are a list of 2 tuples, and in each 2 tuple, each 2 tuple represents an edge, and the edge, and so we have the left node and the right node represented in there, and so that's the edge list represented as a list of 2 tuples. All right. So if you could move on and try the next exercise below. Basically, it's analogous to the first one. Get a single line of code that represents the number of relationships represented. So again, 1 minute. Okay, how are people doing? Can I see your thumbs if you're, give me thumbs if you're ready to move on. All right, I don't see thumbs from everybody just yet, or a big fraction of people just yet. We'll give it a little bit more time. If you run it, if you do something like len of g.edges, that will give you the number 376. That means there are 376 edges that are represented. All right, everybody got that? So, basic statistics of a graph. We have the node set and the edge set. We can ask how many nodes are present and how many edges are represented inside the graph. Okay, so what you've seen just now is the most basic minimal description of what a graph is. It's a set of nodes joined by a set of edges. And they can be represented as 2 lists. You can represent it as a node list and an edge list. And so the node list can either be a list of single elements or it can be a list of two tuples. And if it's a list of two tuples, it means that not only is the node being represented, there's also metadata that's also attached. Likewise, I mentioned the edge list can be represented as a list of two tuples, or it can be represented as a list of three tuples, which I'm going to show as well. And that third element in the three tuple represents the metadata dictionary that encodes the metadata associated with the edge. So let's take a look at that. If I pass in the data equals true keyword argument to the g.nodes method, then I will get back the metadata dictionary that's associated with that node. And so I can use a dictionary to encode all other information that I might want to know, right? So for example, let's say we have a class in this class of 7th graders. We have boys and girls inside the class, and so we have their male and their female gender, and so we can then encode this information. We can even encode things like birth date. We can encode things like where their hometown was and that sort of stuff. Stuff that's metadata that's associated with a particular entity. The underlying data structure is a dictionary of dictionaries for nodes and a dictionary of dictionaries for edges. So you'll be using a lot of the selector syntax when accessing keys and when trying to access values that are keyed on some particular key. And this will become clear as we go along, all right? First thing I would like you to do is to load some data into memory. And so this network data set that we're going to take a look at is a social network of 7th grade students, right? So these little kids were asked to decide amongst their friends who they like, right? And they had like 3 votes, 3 times to vote for a particular person or something like that, or 3 particular opportunities. So this is proximity ratings between students from 29 7th grade students in a school in some place called Victoria. They were asked to nominate their preferred classmates for 3 different activities. A node represents a student, and an edge between 2 students shows that the left student, right, so picked the right student as his answer. The edge weights are between 1 and 3 and show how often the left student chose the right student as his favorite or her favorite, okay? All right, so if we have a graph in memory, there's a few basic tasks that we'll want to do as sort of a sanity check. We'll want to know what are the nodes and how many nodes are present. And so in order to get the nodes from a graph, so note we have a graph that's loaded into memory called G. There's a custom function that I've written. You can find it in the custom functions directory. And so with this graph object, we can ask, how many nodes are present? And the way to do this is to call on the .nodes method. So if I do g.nodes and I run that, oops, let me just run this one. Okay. I'll get back a list of nodes. Now these nodes can be any hashable object. An integer is good, a string is good, a list is not good because the size of a list can change over time, is mutable, so it's not hashable. So in this case, our nodes are represented as integers. There are no names and no names attached. And what's the data structure of this guy that it's returned? It's a list. Okay, good. So let's do a 1-minute exercise below. Can you write a single line of code that returns the number of nodes in a graph? So this one should not be too difficult. Take 1 minute and write that. And at 1 minute point, we'll double check and see how fast people are. Okay, how are people doing? All good? Give me a thumbs up if you're good. All right, so you should have written something like len of g.nodes, and you should get 29. All right? So then we can also get so let's move on from this exercise. We can also figure out who's connected to who in the network by over all of the nodes and that sort of thing. All right? From a broader perspective, so this is no longer practical but more conceptual, I'm hoping to convince you that our usual way of thinking about data, that is the rows of entities and their properties, that we can start thinking about these things in a relational sense, where we have relationships between these entities and not just entities themselves. So it's my hope that you'll take this back home to whatever domain problem that you're working on. And if we have the time, my hope is also that we'll be able to think through statistical problems in network analysis. All right? And statistical problems refer to the summary description of a network plus inference problems, which are a bit tougher. They require a bit of statistical thinking, so I might not go through it today. But there is a set of notebooks inside there that you can use for self-paced learning as well back at home. Okay, before we go on to the actual coding exercises, I want to give you a preview of the tutorial format. You'll notice from Notebook 2 through to Notebook 6, there are pairs of notebooks that have the same title but differ only by student or instructor. Your version is the student version, but you're not prohibited from opening the instructor version. If you ever find the student version exercises too difficult, you can actually look at the answer inside the instructor version. I'm not going to be offended if you do that. In addition, if I'm too slow for you in this tutorial, and you're having a breeze with all of the tutorial exercises, and you just want to self-pace yourself throughout the rest of the tutorial, by all means, don't worry about it. Go ahead. Again, I won't be offended. The notebooks were actually structured and designed to be self-paced learning material as well, especially for this year's updates, so to speak. And so if you want to take the time now to just zoom ahead and do your own thing on the material, totally okay. Otherwise, we're happy for you to join us at the rest of the class's pace. Okay, so with that, we're going to get started with the coding exercises. That's enough of me blabbering on. I'd like everybody to open up Notebook 2 on your laptops and follow along. Now, there's a whole bunch of, like I mentioned, the tutorial exercises and the likes are designed to be self-paced. So the rest of this, I'm intentionally not going to show slides versions of the notebooks. I'm just going to display the notebooks up on there to give you a rough feel for where we are. And I'll do whatever talking I need to do for each notebook and the exercises, but I won't particularly zoom in unless there's a particular exercise solution. Like I mentioned, the exercise solution, you can also find it in the instructor notebooks locally as well. All right? Everybody okay so far? Do we have any questions before we move on? All right, if there are no questions, let's get going. So the first set of notebooks, the first notebook that we'll do that involves coding is notebook number 2, and it's essentially an introduction to NetworkX. Right? It's just to get you familiar with the NetworkX API. So how do we represent relationships between individuals in NetworkX? Or in other words, how do we represent a graph in NetworkX? What I would like you to note is in NetworkX, so what I'd like you to try to do is to count the number of males and females represented in the network. And as a hint, you may want to use the counter object, which I believe I've imported for you at the top as well from the collections module. So we'll spend 3 minutes trying to write this code. And this code will give you a very good flavor for the kind of coding pattern, again, that we'll be using.
How are people doing so far? Okay. Do you have list comprehensions on your mind? That's the hint. You may want to use the counter object, but you may also want to use a list comprehension. Okay. So 3 minutes are up. Can I just get a quick sense for how people are doing? Thumbs if you're done. All right, we sort of have enough quorum to move on. So I'll very quickly talk you through the list comprehension. Note, so if you remember, g.nodes gives us a list of two tuples if we pass in data equals true. Of that two tuple, the first element is a node. We can use the loop variable n and to represent that. And the second element is the metadata, represent a dictionary. So we can use the loop variable d to represent the dictionary there. We're trying to collect the metadata that's keyed on the variable gender inside the metadata.